The Duckosaurus is a custom-built aircraft manufactured to be reliable, easy to manufacture, and easy to fly. It is primarily made out of XPS foam and fiberglass. The plane is a fixed-wing design as well, with a 120-inch wingspan. The weight of the plane, including the payload, is approximately 35 pounds. The airframe features a stall speed of 20 miles per hour, with an estimated range of 10 kilometers, and a turning radius of 75 feet. The plane can fly up to 12 minutes on a fully charged battery pack, with a cruise speed of 33.55 miles per hour. We are also currently looking into using a smaller prop and/or increasing the amount of batteries to increase flight time and range. The plane uses a Turnigy 260 kV brushless motor powering a 20-inch propeller. The motor is powered by an 8S 2P lithium polymer battery pack, which is about 10.4 amp hours total, and the payload is powered by a 4S battery, about 5.2 hours total. The primary payload consists of a camera and the onboard computer. Other electronics include the Pixhawk, servos, RFD 900 telemetry radio, FRR Sky X84 radio, and the Ubiquiti Rocket AC.
Our software system is split into four main components: the ground control station, onboard computer, path planning server, and computer vision server. The ground control station is split into two main components. First, we have a backend web server which communicates with the interoperability server, the onboard computer, path planning server, and computer vision server. We also have a front-end web application used to monitor the plane alongside manual object classification. The onboard computer is responsible for communicating with the camera, cropping targets, and sending cropped images back to the ground control station. To crop targets, we use a pre-trained, faster RCNN model. The path planning server uses the RT star algorithm to generate an efficient path that will avoid obstacles and complete mission objectives. The computer vision server is responsible for taking in cropped images with GPS data and determining their global location alongside target characteristics. It uses a pre-trained unit model to segment the cropped images. Additionally, it uses a pre-trained CNN model to classify shape, character, and orientation from the segmented images. And finally, it uses a KNN to classify shape and character color. We are confident that our current platform will be able to complete autonomous flight and stationary obstacle avoidance with high accuracy. We will attempt automatic recognition of standard targets and manual standard object recognition, but are confident that manual annotation will be successful for targets we detect. We will also be attempting automatic takeoff. We will not be attempting mapping, emergent target recognition, UGV, airdrop, automatic landing, and moving obstacle avoidance.
The team conducted continuous integration with unit tests to verify that our software system remains operational during development. The team also performed developmental testing in small-scale test flights to hone in our focus on single mission tasks at a time. The airframe was designed and validated with the use of both low and high fidelity structural and aerodynamic models to optimize the design and limit the time required for design errors. We also performed structural loading tests with composite coupons and sandwich structures in order to maximize the structural integrity of the aircraft and minimize the amount of material required. Before testing waypoint accuracy, the most important element to ensure safety and accuracy of autonomous flight was tuning. To tune the plane, we had our safety pilot fly in various flight modes, primarily in manual and stabilized mode. We completed 3 autonomous flights with an average of about 2 minutes in manual mode, primarily used for takeoff and landing. The process of tuning included roll and pitch tuning, which required the pilot to make rolling and pitching motions to update the autopilot's parameters for flight. In addition, we are also going to attempt autonomous takeoff as well. We started off by testing out return to home and a simple rectangular mission, then transitioned to testing missions closer to competition mission scenarios.
To test our waypoint performance, we conducted small test missions that contained 5 to 8 waypoints with 3 to 5 stationary obstacles. In this testing, we received 80% of waypoint score on average, receiving an average minimum score of 0.7 for each waypoint and an average maximum score of 0.9. We also analyzed saved telemetry data that was sent to a mock interop server with a grader script that would apply the scoring formula for each waypoint. Here are some of the sample results from the grader script. We flew smaller test missions with roughly 5 to 8 waypoints and 4 to 5 stationary obstacles. On earlier test flights before full tuning, the plane would enter 2 stationary obstacles on average. On later test flights after full tuning and further optimizations to path planning software, the plane would enter 0 to 1 stationary obstacles on every test flight, never entering more than 1. To maximize image quality, the team elected for a camera with a 14.1 square inch resolution at an altitude of 400 feet. Additionally, a camera gimbal ensures that the camera is always pointing straight down. On a testing set of 293 images, the pre-trained faster RCNN model detects target objects with 90% precision. On average, objects are around 90 by 90 pixels, while the original image is 5472 by 3648 pixels. We also simulated blur from aircraft motion in our generated training dataset. To benchmark our detection and classification system, we used TensorBoard to plot loss and accuracy for the training, validation, and testing of our deep learning models. We also generated feature maps to plot the intermediate feature representations for our segmentation network. We also benchmarked our classification and segmentation networks on generated testing datasets as well as 20 real images. We also have an easy-to-use manual operator on our front end that will be used to manually classify all the incorrect targets. To test localization, we performed unit testing on a continuous integration pipeline to verify that camera coordinate conversions remained accurate amidst code changes. We were not able to measure localization error on objects captured from the plane's imaging system. Since we are not attempting the mapping or airdrop tasks, we have no developmental testing for either.
Now we'll talk about our full mission tests that we've done to prepare for competition. So far, our full mission tests have included a manual takeoff, transition into autonomous mode to complete a full waypoint mission, followed by a transition back into manual mode to perform a manual landing. Of the planned tasks we attempted to perform, these full mission tests have covered everything except the object detection and classification task. This task has not been able to be thoroughly tested in a full mission test due to faulty connection cables stopping us from powering on the camera and team members coming down with COVID. This leads to a gap in system coverage, as we are not completely confident that we can take accurate enough images and transfer them down to the ground via our Wi-Fi connection. However, we plan to address this in the final weeks before competition, as we have sorted out all of the issues powering on the camera and will be able to conduct full mission tests that assess our ability to complete the object detection and classification task. We believe that the lack of testing coverage in this task does not threaten flight safety, since any failure in this task does not compromise our ability to fly. All test flights have included ballasts to simulate the weight of all missing components, so the aircraft should not fly differently once we include all of our system. Upon learning that the new competition flight zone is much narrower, it has become a much higher priority to better tune the plane to minimize turning radius. These include yaw tuning, total energy control system tuning, and L1 controller tuning to improve the turning radius. This will help ensure we do not fly out of bounds and better avoid obstacles. Additionally, it should help improve our waypoint score as well. In carrying out our full mission tests, we did run into some issues that were promptly fixed. In one of our first flights, the electronic speed controller overheated, resulting in approximately 10 seconds of lost motor control as the plane glided towards an impromptu landing. However, because it reached the ground, it regained motor control and were able to land as planned. After diagnosing the issue and figuring out the ESC had overheated, we stopped flying for the day and ordered a new ESC that could handle more amps, and improved airflow to the fuselage by cutting out an air scoop. Since this incident, there has not been an issue with any component overheating. In our first attempt at an autonomous mission, we discovered that we were specifying waypoint altitudes incorrectly when the plane attempted to ascend to 300 meters altitude. This was quickly avoided by a manual takeover, and upon diagnosing the issue, we discovered that our path planning software used meters for altitude, while the plan was expecting feet. We fixed the issue on site and were able to fly a correct waypoint mission around an altitude of 300 feet as expected. Later on, we went through our software system and documented all of the points at which unit conversions were required to prevent a similar issue from occurring in the future. As you can see, we have predicted our full mission score to be roughly 31%, without taking into account object detection, classification, and localization, since we have not been able to test this task as a full mission test. We plan on attempting this task at competition with a manual backup for annotating images, so we believe our score will be higher. As you can see, we are not planning to attempt the mapping or airdrop tasks, but we will have done work behind the scenes and plan to attempt these tasks at next year's competition. For operational excellence, we expect full points because we have standard operational procedures for communication and safety checks.